There's a moon orbiting Saturn right now, and NASA says it's one of the most likely places in the universe to harbor life beyond Earth. Methane rains from the sky. Rivers run on rocket fuel. Mountains aren't made of rock, they're made of ice. So here's the question that keeps scientists up at night. If life doesn't have to look anything like what we know, could it already exist on Titan? Here's what NASA has actually found there. And more importantly, what they haven't found yet. Saturn's moon Titan hides one of the greatest mysteries in our solar system beneath its hazy orange clouds. There's a world down there that looks remarkably like our own. Strangely familiar, yet completely alien and beyond comprehension. For decades, Titan's surface remained hidden from view. That is, until NASA found a way to cut through that haze and reveal the moon's true nature. Here is what they discovered. Our first close encounter with Titan came in 1979. NASA sent a robotic spacecraft called Pioneer 11 to visit Saturn and study the rings and moons surrounding the gas giant. Titan's existence had been known for centuries. It was officially discovered in 1655 by Dutch astronomer Christian Huygens. Observing Titan is straightforward enough. As its name suggests, Titan is a large moon. It's actually slightly bigger than the planet Mercury and about 50% wider than our own moon, but it's still incredibly far away. So when Pioneer 11 first reached Titan, scientists were intensely curious to learn what the moon actually looked like. The spacecraft, however, could only see the thick orange clouds that completely surrounded it. Those clouds were impenetrable. What Pioneer could do was investigate what that haze was made of. And it found something remarkable: a dense, nitrogen-rich atmosphere. This was strikingly similar to our own atmosphere here on Earth, which is also mostly nitrogen. But another discovery on Titan truly ignited the curiosity of scientists. So what are hydrocarbons? Technically, they are molecules formed when carbon atoms bond with hydrogen atoms. Most of us encounter hydrocarbons almost every day in the form of fuels like gasoline or propane. Titan's atmosphere is saturated with methane, what we typically refer to as natural gas. Why does this matter to NASA scientists? Simply put, these carbon-based structures are not only useful as fuels, they are also known as the building blocks of life. Critical molecules like DNA and proteins are built on hydrocarbon foundations. Now here's a word you might find more familiar: hydrocarbons. Functionally similar. And they also introduce oxygen into the atmosphere. So if we can find oxygen on Titan, we wouldn't just have the building blocks of life. We'd have the fuel to sustain it. And here's something worth knowing. There is already a small amount of oxygen on Titan right now, but to find it, we'll need to go much deeper. So stay with us. There's a lot more to uncover. A spacecraft flyby close to Titan also gave us insight into the moon's gravity. And it turns out to be a little strange. Titan has significantly less gravity than you'd expect. Despite being much larger than our moon, Titan's gravitational pull is actually slightly weaker. This tells us that Titan isn't very dense and isn't made entirely of rock. That opens the door to some fascinating possibilities. The combination of a dense atmosphere and low gravity means that a person in a wingsuit could leap off a cliff and glide through the air like a bird for as long as they pleased. It also makes flying vehicles an ideal tool for exploring Titan's surface. Let's look at what NASA found back in the 1970s. Hidden in the outer regions of the solar system was an abundance of material strikingly similar to what we find on Earth. Beneath Titan's clouds, there might be a discovery capable of rewriting everything we know about life and the universe. But it was so close, and yet so far. They had to wait for the technology to catch up. And 25 years later, in 2004, the Cassini spacecraft finally reached Saturn and picked up right where Pioneer 11 had left off. This was a joint mission between NASA, the European Space Agency, and the Italian Space Agency. Cassini was equipped with radar and infrared scanners capable of penetrating both Saturn's and Titan's dense atmospheres. Over the course of its 13-year mission, the spacecraft made 127 passes over Titan using its onboard instruments to cut through the haze and map the surface. And what it found was extraordinary. Titan is the only moon in the solar system with an atmosphere, and that atmosphere is 4 times denser than Earth's. This creates a kind of reverse greenhouse effect. Very little heat from the sun can actually reach the surface. As you descend toward the surface, all the methane gas in the air gradually cools, condenses, and liquefies, falling like raindrops onto a surface covered in ice as hard as granite. Titan's average surface temperature is minus 179 degrees Celsius, and the freezing point of methane is minus 182 degrees Celsius. This creates the perfect environment to support a complete hydrological cycle. Except instead of water, it runs on rocket fuel. The result? Rivers, lakes, and seas flowing across Titan's surface, making it the only known world beyond Earth with stable liquid on its surface. The team that built Cassini was remarkably forward-thinking. They knew Titan would reveal something extraordinary. So the European Space Agency added a secondary probe named after the Dutch astronomer who first discovered the moon, the Huygens lander. It was designed to slowly descend to the surface by parachute and capture photographs of Titan during the descent. In January 2005, Huygens began its descent. Based on imagery from Cassini, the intended landing zone had been identified as the shore of a small lake. The probe was built to safely land across a range of terrain types, from mountain ranges and flat plains to liquid oceans. Its battery was designed to last 3 hours, with 2.5 of those used for the slow parachute descent. And when Huygens finally broke through Titan's clouds, here is what it saw. Between brighter mountain ranges, a dark valley was beginning to take shape. As it approached the surface, we could clearly make out a network of drainage channels and stream beds carved into the sides of the mountains. Some hundreds of meters wide and several kilometers long. These had been carved by methane rain flowing down into the valleys. Huygens was descending directly toward the center of this dark region. As it got closer, it became apparent that this wasn't a liquid surface after all. Huygens was actually landing in a dry riverbed. Upon touching down, the probe created an indentation about 12 centimeters deep, then bounced and slid forward roughly 30 to 40 centimeters before wobbling to a stop. When the cameras began scanning the surface, the most striking discovery wasn't how alien this world looked. It was how familiar it felt. Strip away the orange tint, and it could pass for the bottom of any riverbed on Earth. We see large, rounded rocks worn smooth by flowing liquid, surrounded by smaller pebbles, with what appears to be a sandy surface beneath them. But these aren't rocks. They are chunks of frozen water ice, as hard as stone. The mountains are made the same way. And remember, water means oxygen, H2O. But in frozen form, it's of no use to life. The muddy-looking surface surrounding the probe turned out to be a strange hydrocarbon material that scientists described as snow-like. A thin, brittle crust on the outside with a softer texture underneath. As the camera looked out over this alien landscape, we began to notice ripples in the air. This was heat from Huygens' lamp causing evaporation on the surface. At one point, you could even see a tiny droplet of methane dew drift across the lens. As the camera tilted upward, the sun appeared in the sky, just 1/100th as bright as it appears from Earth. Even though it was midday on Titan, the light was no brighter than twilight back home. What Huygens found was genuinely impressive. But it couldn't uncover Titan's most intriguing mystery: liquid methane. The probe seemed to have landed in the right place, just at the wrong time. So where had the liquid gone? One of Huygens' interesting findings concerned the moon's methane cycle. We're familiar with the water cycle on Earth. Water evaporates from the surface, rises into the atmosphere, condenses into clouds, and eventually falls back down as rain. On most of Earth, rain is relatively frequent because energy from the sun continuously drives evaporation. But on Titan's surface, so little sunlight reaches the ground that liquid methane evaporates extremely slowly. When evaporation does occur, all that methane vapor accumulates in an incredibly dense cloud layer that can hold enormous quantities before any rain falls. The result would be long drought periods potentially lasting hundreds of years, followed by intense downpours capable of triggering flash floods across the entire moon. Unfortunately, we haven't been able to visit Titan during its rainy season, but that doesn't mean the surface is completely dry either. Throughout its 13-year mission, Cassini continued observing Titan and gathering data about its surface. What it found was this: during the dry season, liquid methane was confined primarily to the northern polar regions. The spacecraft learned to detect the glint of sunlight reflecting off these areas, and that's how the first liquid methane lake on Titan was identified. It was named Ontario Lacus, inspired by Lake Ontario in North America, because the two were nearly identical in shape. Titan's lake was about 20% smaller than Lake Ontario, yet still covered roughly 15,000 square kilometers. Despite its size, it was relatively shallow, averaging somewhere between 40 centimeters and 3 meters in depth. It was also strangely calm. The surface appeared perfectly flat and glassy. We don't currently know why. Given the higher atmospheric pressure and lower gravity, you'd actually expect waves on Titan to be larger than on Earth, and Lake Ontario certainly produces substantial waves. Near Titan's North Pole, there's also a small ocean called Kraken Mare, roughly 400,000 square kilometers, slightly smaller than the Black Sea on Earth. It's large enough that the gravitational pull of nearby Saturn creates a tidal effect, with liquid methane rising and falling by as much as a meter. Despite its size, Kraken Mare is still relatively shallow, with an average depth of around 300 meters, compared to over 2 kilometers for the Black Sea. But the active processes on Titan aren't limited to methane lakes and oceans. There are also volcanoes, except there's no actual rock on the surface. What looks like rock is ice. So instead of erupting lava, these volcanoes erupt a slushy mixture of ice and water. But how can any liquid water exist on a world this cold without freezing solid? It turns out this icy volcanic magma is mixed with ammonia, which acts as a natural antifreeze. You probably know ammonia as a foul-smelling cleaning product, but it was incredibly abundant during the formation of our solar system. This simple compound, combining nitrogen and hydrogen, two of the most common atoms in the universe, gradually became incorporated into the structure of planets and moons, playing a critical role in shaping those environments. Any ammonia on Titan's surface would have evaporated, contributing to the formation of its nitrogen-rich atmosphere. The ammonia below the surface, however, combines with water ice and allows it to melt into various liquid states. If we imagine a cross-section of Titan, at the very top, there's a solid crust of frozen ice. Beneath that is a partially frozen slushy layer that periodically erupts through volcanoes. And below that slush, scientists believe a thick layer of liquid water still exists above the moon's rocky core. Residual heat and ammonia are thought to be sustaining this subsurface ocean. So we have water and we have hydrocarbons. Put those two together, and you get carbohydrates, the fuel of life. And thanks to active volcanic processes, there are opportunities for these two components to interact with each other, both above and below the frozen surface. We're not saying there are aliens here, but we can say that the conditions may exist for the most primitive forms of bacteria to develop, meeting the basic criteria for what we would scientifically classify as life. The environment is there. This is exactly why NASA is investing hundreds of millions of dollars in a mission called Dragonfly, a return to Titan. Dragonfly is a nuclear-powered helicopter drone designed to fly across Titan's surface and collect samples, which will then be analyzed in an onboard mobile laboratory. The plan is to launch Dragonfly in 2028 and have it arrive at Titan in 2034. It will be an extraordinarily complex mission, but it may be NASA's best and only real shot at unlocking Titan's secrets. Personally, I think it's also worth considering this. This vehicle could potentially carry plant or microbial life to Titan and test how it responds. Let's see what the years ahead reveal. Thanks to Dragonfly, we'll finally learn what that sandy, snow-like surface is truly made of. And if there are any signs of life, if we can confirm and prove it, this may be our best chance to understand it. As we mentioned at the start of the video, this channel is still very new. If you enjoyed this video and want to see more like it, please show your support. We're counting on it. Thank you all so much, and we'll see you in the next one.